Great, very good. Thank you everybody for being here. It is a great honor to have Gemma de las Coves this week in our seminar. I saw her speak at a conference once, and I sent her an email saying that I really liked her work, and we've been in contact ever since. I visited her group multiple times. They do an incredible range of things, from mathematical quantum physics to computer science. They even are bold enough to talk about biology sometimes, and every time I meet her, there's something new. So I'm very excited what she'll talk about today, and I don't want to spoil it too much. So Gemma, the floor is yours.
Okay, thank you so much for having me, and to all of you, good morning. Thank you for coming. So I'd like to share with you some of our struggles to understand some notions of universality. And our story starts with the realization that there are some spin models on the left, which appear simple. For example, they are the 2D Ising-With fields. Yet, when seen in the appropriate light, that's a metaphor, they can behave like, that is, they can mimic the behavior of any other spin model, such as models with Q-level spins, where Q is larger than 2, or with many-body interactions, or with on higher dimensional lattices or graphs. So all those distinctions that we thought, and they are in a sense important, such as the dimensionality of the lattice, the symmetries, and all of that, are washed out from this perspective. And so the 2D Ising model with fields in particular is universal in this sense. It can simulate any other model, but in fact, we realize that most spin models are universal, and somehow the 2D Ising-With fields is kind of the simplest. And we also found out sufficient and necessary conditions for such universality. And obviously, we all love the most remarkable and influential universality result, I would say, well, at the very least in computer science. I mean, as you know, it was first the concept was developed of a universal Turing machine, and then it was implemented and engineered, and it revolutionized our world. As you very well know, there are fixed Turing machines that can run any algorithm. So initially, you might have thought that there's such a thing as the algorithm, that is the set of transition rules, and the data that's fed to the algorithm, and that's either accepted or rejected. But for Turing machines, the algorithm can be encoded as part of the data. They can be encoded as a bit string, and that's why a fixed machine can run any algorithm, because it can read the description of another machine and behave like it, mimic it, simulate it. So that's the very important, let's say, discovery, realization that there are such things as universal Turing machines. You may know that for simpler types of automata, there's no such universality. For linear bounded automata, Kusaman automata, or finite state automata. There's a similar result for neural networks, and in particular for Boltzmann machines, for restricted Boltzmann machines. You can make the statement that for any function that's well behaved enough, meaning it's continuous or maybe something slightly stronger than continuity, there is a size of the number of hidden parameters in your network, your say restricted Boltzmann machine. Sorry, and at the beginning I should also have said, and for any epsilon, for any target function, and for any epsilon, there is a size of your neural network, and choice of the parameters of the hidden units, so that the neural network behaves effectively, or like is epsilon away from that target function. That's something called the universal approximation theorem, and it's very similar, in fact, to spin models. And for the first time, I can make this very precise, and I will very mention that at the very end of my talk. Now we have a result there. After many years of suspecting, the results look really similar. Even the proofs are very similar. And now I can say they are essentially the same. But I'll get there at the very end. So these different results have been named universal, but there are other things that are universal in mathematics and logic in the world. So they are not only, it's not only that they are called universal, but they also share some similarities. And if I start explaining to you the similarities, I will not get where I want to go. So I'd like to present some results, and I will hopefully convince you of this similarity. But in fact, it's a bit difficult, honestly, to make that precise. So we've been trying to understand how precisely are they related. I think it's a worthwhile question because universal Turing machines are 100 years old and are so important and influential that if what we discovered for spin models is actually in some hidden way the same, well, that's quite interesting. If it is not, then I think that's interesting too. Why should there be such a structure within spin models, and what is the scope of that structure, and what other places can we find it? Spoiler, right now our understanding is that they seem to be different notions of universality. So the one of Turing machines seems to be stronger than that of spin models, but I'll walk you through there. And another thing that fascinates me, even since reading Gödel and Schabach, maybe many of you have read it as well, by Hofstadter, is very, very powerful attack of self-reference and negation, which can give rise to very far-reaching results, such as Gödel's incompleteness theorems, or in fact, Cantor's theorem or Russell's paradox. I'll mention some of this later. And I think that all such results of uncomputability, undecidability, and so on, we call them unreachability. They are in a formal sense all the same. And they are linked in a sort of love-hate relation with universality. I'll try to share with you some of that. So the overall goal is to understand the scope of some notions of universality and of unreachability across physics, computer science, maybe logic. And I spent a lot of time in recent years reading philosophy, and that's very muddy. It's very complicated over there, but I'll try to say something here. So I'm Gemma. I spent the last 17 years in Innsbruck and Munich mainly, but I just moved to Barcelona. I'm at the Universitat Pompeu Fabra. If you ever want to come, say hi. And I'm also an ICREA professor, which is a really great program. I feel like I'm in paradise, really. But I'm really glad about that. So in order to share with you some of our struggles with trying to understand the scope of universality and unreachability, I would first like to share with you some ideas, then some concrete results on comparing spin models with automata or formal languages. And then maybe the most ambitious project has to do with developing a framework for universality that's supposed to encompass all results we know. So if we talk about universality, we need to start with the question of what does universal mean? And it is an adjective that means relative to the universe. And as a frozen metaphor, it means all-encompassing. this can be made precise in what we call the basic structure of universality, which just formalizes this idea of being all-encompassing, where given a collection C and a relation R that lands in C, that is to say, so a relation is like a subset of a Cartesian product of two sets, right? It's like the subset of pairs where the relation is true. Right? So when I say that the relation lands in C, I mean that the second component of the Cartesian product is C. So given a collection C and a relation R that lands in C, something U is universal if U, C is in R for all C. That is to say, if U stands in relation to C for all elements in C. Okay. That's very, very basic. I'm not saying that R be transitive, that that's so basic that it's more or less impossible to do something meaningful with that. But that's maybe a takeaway message here is that universal is relative to a set, kind of this target set, and a relation, R, right? So all encompassing. Encompassing is the relation R, and all will be a statement about some set, C.
So you mentioned that the second item from these pairs has to be in C. Doesn't U have to be in C as well?
No.
Okay.
It need not be in C. That's a good question. Intuitively, if U is in C, then the notion of universality may be stronger. It may be more interesting.
But which Cartesian product are we looking at then? So we're not looking at C times C then. We're looking at something.
Yeah.
Something times C.
Yeah, unspecified.
Okay.
Can I give you a radical example of that? Okay, that will take me a minute. Have you heard of the problem of universals in metaphysics? It's the problem by which people ask, by virtue of what can we assign the same attribute to different particulars?
Right.
For example, I can say that this is brown and say this is brown. And then there are two main camps, and the metaphysical realists would say that we can assign the same attribute to different particulars because they are both instantiating a so-called form or universal or idea that's existing somewhere outside of space and time. Yeah, it's very intimately related with our space and time. So that would be along the lines of Plato or Aristotle. So you see, in that will also instantiate this structure, but clearly we don't want to accept that U is a physical thing. And now that's a connection with unreachability. If something claims or purports or aims to be all-encompassing, well, how about itself? I mean, encompassing yourself is not yet contradictory. It's as if I were to say, I am honest, I am right now telling the truth. That's all right. The problem is that if you encompass yourself but kind of compose that with a function without a fixed point, such as negation. Negation is the simplest function without a fixed point. Like when I say, I am lying to you right now, you end up in a contradiction that I am lying if and only if I am not lying. And it's very interesting, let's say, how different intellectual endeavors react to that contradiction. But the short story is that nothing can encompass negation of itself consistently. So there you go. That's kind of a limitation, let's say, of universality. So unreachability, let's say, for the purposes of this talk, and for us, we can make it a bit more precise, but it is the fact that no system can thoroughly talk about itself. Try to explain that in a second. So let me explain that for sets. We will land in, that will be Cantor's theorem. So for a system, take a set S. And by talk, so assume that talk means describe an attribute of that set. That is to say, so an attribute is a map from that set to 0, 1. So it's a Boolean function, if you like, so that an element of the set will be mapped to 1 if it has that attribute, and it will be mapped to 0 if it doesn't. For example, say that the set is the set of natural numbers, and the attribute is being a prime. And every prime number would be mapped to 1, and every composite would be mapped to 0. Now, crucially, let us identify the attribute with its extension, what mathematicians say, right? So that is the set of elements where it is true. That is the set of elements in S that are mapped to 1 under F. Now that's clearly a subset of S, right? In other words, it is, if you like, an element of the power set of S. For example, say that the set has 3 elements, then its power set has 8 elements, so it has 2 to the cardinality of S elements. And now that the statement is of unreachability in this simple case is that a set can never be put in one-to-one correspondence with its power set. So there can be no bijection. What's important is that there can be no surjection. That's very, very deep and very far-reaching because it holds for any set. One way to prove it, say, for example, how Cantor proved it by a diagonalization, which is the same thing, is by contradiction. So by assuming that there is such a surjection, and then looking at the diagonal is like self-reference, you know, like the sets and their tags, like self-reference, and then flipping the diagonal, that's like negation. And then the new element is not in the list by construction, so the initial function could not have been a surjection. So, but another way to put it is that this attack of self-reference and negation always gets you out of the system. It can never be captured from within the system. So S can never encompass, can never reach P of S. The most exciting things I've learned in the past. Pervasive this attack is. So the fact that like it has consequences in so many fields. This sentence is false, is the very same attack. The halting problem can be proven by assuming that there was a machine that solved the halting problem, feeding it its own source code, and flipping the results so that if it halted, it wouldn't halt, and if it did not halt, it would halt, and then the resulting machine would halt if and only if it would not halt. That's an inconsistency that we're not willing to take, to accept, so we reject the assumption that such a Turing machine existed. Gödel's first incompleteness theorem constructs a sentence that says, I am not provable. There exists no proof for the sentence whose Gödel number is myself. Russell's paradox, the set of all sets that do not contain themselves. Does it contain itself? It does if and only if it doesn't. Now we expect from a set to either, we expect from the relation between a set and a member to, or an element, to either be in the set or out of the set. It cannot be in if and only if out. That's an inconsistency that we're not willing to accept. So we have to reject naive set theory and no longer posit that for any property, there is a corresponding set of elements with that property. Because, hey, Russell gave us a property, and the purported set with that property is inconsistent. And Tarski's undefinability of truth is the same thing. There cannot be a predicate that gives you the truth of sentences that could be fed to itself and negated, and that would be a problem. Cantor's theorem, it's the same thing. It's very far-reaching because it is not the case that if you reach a high enough level of complexity, this problem goes away. But on the contrary, just no matter how incredibly complicated your set is, the power set will be more so. So it entails, for example, that there are infinitely many types of infinity. Before Cantor, we all thought that infinity was anything. There's finite and infinite. But it's not only that it's not anything, but there are infinitely many types of infinity. And that is incredibly far-reaching fact can be proven with the attack of self-reference and negation.
I understand that the power set is there's never a rejection, so the gradient always increases, but I'm not entirely sure. I don't entirely understand the relation between this fact and these paradoxes you mentioned. Like, in what sense can we understand like this sentence is false as a paradox to be explained by this power set for the net?
So this is maybe not apparent from what I was, the way I was putting it, but it is all apparent in this little known theorem called Lever's theorem. It was written in a pretty obscure category theory paper and readable in my eyes, unfortunately made accessible by Janowski in 2003. And so the first part of the answer is they have a common skeleton and it's neatly identified in this theorem. The second part of the answer is that via I am a liar, you can create a contradiction when trying to show that there is a surjection from a set to its power set. We don't want to accept the contradiction, so we reject that there was a surjection. So for Cantor's theorem, the liar paradox is a way to prove, unfortunately, it's a proof by contradiction. Not very good, but I think it's also not very satisfactory because it also gives the impression that the problem is just one element, but in fact it's the opposite. Like most elements are outside the scope of any injection. Like it's actually, the image is like a zero measure. Yeah, but that's how that's usually done. Okay, and this is a...
Sorry, are many of these things proven by contradiction?
This is not a statement.
Not really
The first thing is not a
theorems,
statement. The first thing is not a statement, right?
Yeah,
So yeah, there's a mixture of statements and of
because they
paradox.
are, in essence, they are contradictory. They're all contradictory.
Are you wondering if there's constructive proof of Cantor's theorem?
Yeah.
There cannot be, right? But there's the whole point that there's no such thing.
Yeah.
What would the constructive proof be? The point is there's no surjection.
Well, so the thing is, we're proving a theorem by contradiction, and there are people in the world who do not like that.
Yeah, that's true.
I mean, we have one here, but
No, obviously, I was just thinking that if these type of contradictions exist and they come about in so many different settings, then maybe sort of invalidates the whole proof by contradiction. Because
Of course, we have to go through this. This is of course an old-fashioned Dutch tradition with Brouwer, Brouwer's fixed-point theorem. That guy, he didn't believe in proof by contradiction. So he set up this whole school of trying to prove everything in mathematics by building everything constructively. I have no idea how far he got. I mean, he ever.
Okay, maybe I can help a little here. Because Lovier's theorem has a counterpositive, which is precisely stated in terms of a fixed point theorem. Right. So, for example, you would look at the proof that the halting problem is uncomputable, and I would presume that that would be stated in the following terms. For Turing machines, there is a fixed point. What is the fixed point? It's the non-halting point. Because if you compose a non-halting algorithm with another one, it stays non-halting. Okay, maybe that was a little obscure, but I'm trying to say that half of the paper of Janowski is precisely phrased in terms of the contrapositive. It's the same statement, right? The contrapositive of Lovier's theorem, and which is a statement in terms of fixed points, and that should avoid proof by contradiction. But I'm not sure about contradiction. I'm not sure how I would come about in terms of some fixed point for sure. Okay, and then I discovered this wonderful book called Beyond the Limits of Thought, by Graham Priest. And it convinced me that, as well as some introductions to metaphysics, that this kind of attack can be used to limit what can be formalized. I think that's pretty clear. For example, with Gödel, right? I mean, one of the common readings of Gödel is that it shows that probability is a different notion than truth. You could say that truth cannot be, in some sense, formalized. Anyway, or computed, clearly with halting, or learned. That I didn't mention, and honestly, I never studied that very carefully, but I think there's something called Gold's theorem, which should be something along the same line for where the task is to learn a formal language. Known, the sentence is false is used as an attack on certain theories of truth, like correspondence theories of truth. And then some bring it as far as to end up denying that an external reality exists. That's according to some of the introductions to metaphysics I read. I guess it depends on how much you like that argument. But I'm trying to illustrate the kind of leverage that the thrust that paradox has in different endeavors. Yes, that's the one. And as usual, we can go back to the ancients and consider Archytas. He was a Pythagorean, and he considered the absurdity of reaching the end of the universe and stretching out an arm. That's clearly absurd, because if it's the end, there's nothing beyond. But it also, if it's the end, what is it bounding? Is it bounding what is with what is not? What is not a thing. So you can argue along similar lines way more carefully than I just did, and let's say examine various philosophical difficulties in the light of trying to reach beyond an ultimate limit, and how contradictory that is. That's partly what Priest does in this book. So it is paradoxical to claim that something is unreachable or inconceivable or unthinkable or ineffable. So let me give you some of my favorite examples. Say Parmenides said, what is not cannot be nor be thought of. Yet here we are thinking about it. Nothing can be known, the skeptics would say. Well, then neither should that very sentence or that very statement be known. Everything is relative. Well, then so should that very fact be relative, or is it outside of that, of the scope? But why is it supposed to have a different status than that everything that it is concerning? Or something is indescribable, but that right there is a quality, indescribable. Or, and with an omen, something cannot be predicated, but we just predicated. There's something very delicate and somehow very wrong about trying to reach out beyond an ultimate limit, beyond something of which you cannot know. So Priest talks about the limits of cognition, conception, expression, and iteration. I love that book. And in my eyes, it gives an entire kind of philosophical dimension to the paradoxes of self-reference and negation. In fact, Priest proposed something called a schema T, which is like, it's very clear. It's a schema, let's say, based on these three principles. So say that something is contained within a set and call that closure. At the same time, say that something transcends that set, call that transcendence. And at the same time, this something exists. That's a contradiction, because we don't want to accept that
Someone trying to ask a question.
Alexandru, can you maybe mute your computer?
Or
Or are you trying to ask a question? Great.
so if something exists, it cannot be outside and inside something at the same time, right? There are some properties that we require of existence. So that's why it is a contradiction. And essentially all endeavors based on logic, what they do in front of this contradiction is deny existence. Right? Like Cantor's theorem, say there exists this rejection. I'm not sure how to put it, but I'm sure it can be put there. Yeah, there exists a surjection. I think that would be kind of, or that would entail closure, because that would say that every element in the power set is in the image, or is kind of encompassed in the image from the set, from the surjection of the set. But then if something transcends, that's probably the self-reference and negation, right? Like a kind of the new element that you construct in the diagonal and you flip it. And but then this rejection cannot exist. Yeah, because it's not a surjection, you just found an element outside of the image. So they deny existence. And that has very far-reaching consequences. I should say that I believe that Priest has been advocating, has been wanting us to use a different kind of logic that can cope with contradiction. That would be paraconsistent logic. But by far, the usual answer is no, we don't want to accept it. Which I think is a bit short-sighted. Obviously, philosophy, the field is much more open. It's unclear. Let's say different thinkers would take it from different angles, and it's unclear what one should do with that. Or not unclear, I should say. It would depend on the thinker. Interestingly, people tend to jump to conclusions about the physical world from the logical world. And I think that's also often premature and unjustified. I still think that I am unclear on what the consequences of these contradictions are for the physical world, because I am unclear on the relation between abstractions and the physical world. I have a few examples there which I think are quite interesting. And quite interestingly, many artistic expressions are not bothered at all by these purported limitations. My favorite example may be Fellini's 8½, where the entire movie is self-referential, and there are many paintings, and it's not a problem with them. So I feel that they are way more open-minded than you would have to be. So if no system can thoroughly talk about itself, nothing can be ultimately universal, and this is the tension. I'm starting to write a book about that to put it in as clear terms as possible. Okay, so, and I think it has some philosophical implications, like the fact that there is no ultimate closure. But I never like this. I never like these attempts to assume that the whole universe is described by a wave function. It seems to me to be wrong for various reasons. But I was inspired by this lack of ultimate closure to also argue that that must be wrong. And I also care a lot about a fascinating thing, which is our minds and the fact that we can engage in self-reflection, and we seem to enclose and transcend ourselves, and I think that makes us really special. And if I'm not mistaken, Hofstadter and Gödel-Escherbach argued along those lines as well. I think it was a theory of consciousness, but based on kind of a strange loop or a tangled hierarchy. I believe that must be related. So that all of that is to say that science is here ignoring or forgetting or not explaining some very remarkable fact or logic about his existence, which is that we seem to have thoughts, think about ourselves, and all of that is at the moment left out. Although I guess that with AI we'll be able to learn more things about many of these ancient questions. Okay, so I'd like to now move to a way more safer terrain, more technical. We are now in this realm of mathematics, and our goal is to compare, first of all, spin models with automata. Remember, the ultimate goal was to compare their universalities, although we didn't quite get to the end there. This is more of a bottom-up approach, in the sense that we have two examples that we understand well of universality. We try to compare them directly. The framework is more of a top-down approach. So spin models are mathematical objects, so are automata. That's good. It's a good start. Yeah, they appear different. Spin models are essentially functions from spin configurations to the reals for energies. Automata, they have this ugly definition. The Turing machines, a 7-tuple set of transition rules, a start symbol, final symbol, holding state and accepting state and so on. But anyway, it's a mathematical thing. So how can we compare them? Well, we did the following. You may like it more or less. We did the following. We cast spin models as formal languages. You know what's a formal language? The kind of thing that the Turing machine accepts. So it's a subset of sigma star, where sigma is a finite alphabet and star is the clean star. So it's the concatenation of symbols from sigma of any finite length. Any, that's quite crucial here, any finite length. And then we found that classical spin models are context-sensitive languages. So we classified the image of such classical spin models in the so-called Chomsky hierarchy. And that's what we found. So I'll tell you more in a second. And I've been trying to make this precise, but this work is unfinished. It seems then that universal spin models would correspond to a type of pseudo-universality for linear bounded automata. That is to say, a weaker type of universality than that of Turing machines. But so let me explain the first part. So a spin model H is mapped to a formal language L sub H, where a spin model is a map from a domain to energies.
So you have to tap the screen twice. Make it
Did
big.
I do something wrong?
Yeah, if we tap the screen twice, then it becomes big.
And look, the language of a spin model H will be, LH will be the set of all pairs x, comma, h of x, where x is in the domain of h. That is to say, it is the graph of the function, the set of all pairs where it is true one. It's the graph of the function, that's what it's called, okay? For instance, the 1D Ising model is a map from, imagine that this is +1 -1, right? So S1 is a spin number 1 to spin number n, and a configuration here, that is to say, for example, +++++ is mapped to a number, which would be the sum from I equals 1 to n-1 of the product of Si times Si plus 1. So this is like a parity interaction that would give us +1 or -1, and we would add or subtract them, and we would get a number between n and -n or something like that. Crucially, in our definition of a model, this is the case for all n. This is absolutely crucial. This is a family for all n, because if we take a finite n, the corresponding language would be finite. And as you may know, everything is trivial in formal language theory for finite languages. They are all regular. I think that's a shortcoming of formal language theory. That's where we are. So the language of the 1D Ising model would be the set of all such pairs, S1 to Sn, followed by an energy. There will be an encoding, right? There are some conventions that need to be fixed, but they don't change the result. This for all n. So because it's for all n, this is an infinite language. And then we classify LH in the Chomsky hierarchy. And we prove a theorem. For example, such LH is deterministic context free. So you can like more or less this step, but once this step is done, or like we can talk about conventions, for example, about how spins are ordered, how the energy is encoded, if it's in binary or if it's in unary, things like that. But once this is fixed, this is a theorem. Like you can classify the language, and that cannot be discussed as long as the proof is correct. And as a byproduct, we obtain a new complexity measure for classical spin models, which is different than the usual one based on the computational complexity of the ground state energy problem. Which I like to say that it captures the hardness of the grammar of physical interactions. Yes.
Does this new complexity measure somehow correlate with others?
Yeah, we can compare it.
Right.
I'll compare it in a minute.
How can we compute this measure?
Good. We prove the theorem.
Yeah, but if I want to compute this measure in a real spin model, how can I compute this complexity measure?
You need to prove a theorem as far as.
No, I can compute.
I mean, proving a theorem is a computation. I'm not sure what you mean by that. So usually these things are proven by using the pumping lemma.
No, I mean more like I get the data and I have a phase transition. I can compute where is critical points kind of thing. So
then I have an order parameter. That's what we're doing easy, like if you don't do theorems. So if you define a complexity measure, how can I go back to the data and compute that measure? Like an order parameter is also theoretically proven that defines phase transition, etc. How could I go back and compute it?
I don't know. That's a short answer.
So I guess if you propose on any particular spin system, then that's not something that has for all n in there,
Ah, okay.
right? So
Okay.
then it's all trivial. Then it's all the lowest complexity, any particular spin system, I guess. Is that true?
Sorry?
So if you have a particular spin system, that is necessarily like a trivial then,
Yeah,
because it's a particular,
which is an absurd conclusion.
even if it's infinite.
What does-
One particular infinite spin system.
No, one particular. What does infinite mean? So, this world of formal languages is the world of the potential infinity. If you've heard of it, this is like an Aristotelian distinction. Potential infinity is something that doesn't have a bound. It can always grow. This is the natural setting of bit strings, for example, right? Or number of times that the head of the Turing machine can operate. Finite, but unbounded, and infinite. The infinite per se, or whatever, might be identified with the actual infinity from Aristotle, which is, he would say, is there all at once. I would say it's something like the set of natural numbers, something that already has a cardinality, which is infinite, as opposed to any natural number. Any natural number, I think, would correspond to the potential infinite.
Oh.
Anyway, my point is that here, so I'm trying to make sense of your statement that this is infinite. What does that really mean? I think what makes sense is to consider such families for all n.
So you're not focusing one spin model is like a cardinality of real numbers is different from cardinality of natural. So you mean that when you consider all the classic spin models, there is a complexity measure that is not known, and then now you label it. So how can we?
Maybe if I'll show you the results, it's a little more clear.
Can I add something?
Yeah.
What is the meaning of the, because I'm not so familiar with languages, what is the meaning of the fact that LH is deterministic? And then I have a second question. Does this work only if you, I guess you need H of the set of spins to have like a regular form that you can generalize when you increase n, right? So if you, you need something that is somehow easier recursively defined, or like a general form that you can just say, oh, if I take n large, it's has the same form.
So let me start with the second question. It's a lovely question. Indeed, make any statement that concerns an infinite amount of things, you need some sort of generator, a finite handle. Otherwise, you cannot even make the statement. So here, they would be the local form of the interactions, which in fact we consider them to be very general, but ultimately there must be some sort of finite description that can be applied an unbounded number of times to even talk about that so-called model. And for the first question, let me answer it in the following slide. So formal languages can be regular, deterministic, context-free, context-free, context-sensitive, recursively, and reliable. That's a hierarchy. RE languages are recognized by Turing machines. Linear bounded automata recognize context-sensitive languages. Push-down automata, context-free, deterministic push-down automata, deterministic context-free, finite set automata. So this is a model of computation, this push-down automata, which is a head that cannot overwrite the tape and can only move left to right. It has a stack, in German, Celler. A stack that is like first out, last in, right? So like it's one-dimensional. It's crucial that it's one-dimensional, and you can put things on top, and then you can retrieve the things from the top. And if that machine can have non-deterministic transition rules, it can do more than if all of their rules are deterministic. What's beautiful about that is that they all have a grammar, a generating grammar. It's called a regular grammar, context-free grammar. In fact, for the grammars, you cannot distinguish these two: context-sensitive grammar and restricted grammar. And yeah, it's really nice to see kind of the generating mechanisms. It's another way to see this finite handle of infinite means. Anyway,
So to show that it's deterministic context free, we map it to the cellular automata that has the specific properties that it is deterministic.
yes, it's not a cellular automaton. It's a
Sorry, the automaton trying
Yeah,
to.
yeah. Okay, so what we found is that any 1D spin model, its language is here, deterministic context free. 0D spin models,
That's what you mean, the complexity, that I didn't get in the previous slide, because complex could be order parameter you're measuring the system, but you mean the complexity within the hierarchy of languages.
yes.
Okay, thanks. Then I understand. I retract my question.
Can I have a naive question? Because I am not so much used to this framework. So in physics, you can define arbitrary Hamiltonian, so the H, but we are only focusing on the class of Hamiltonian which have some inherent symmetry. So like Z2 symmetry or ON symmetry, because this is how to say the most comparable to reality, like physical system. So can I put like, if I have for instance, I see in just like 1D spin, I put it into deterministic context free. Where can I put like ON model into this picture?
Okay, so two answers. One is that we don't have any symmetries, or like the models on the left. Okay, let me complete that. The models on the left could have a symmetry or not, and that doesn't make a difference.
Why does it not make any difference?
It's interesting. Not sure. Maybe I move on because I'm a bit late.
Good
But
question.
second part of the answer. ON. No, the configuration space is discrete so far. So the
But we
space.
also have something like multiple state analog of ON. Like you can also have
Okay.
a port model or
Yeah, the POTS model, that's all fine. That would apply then.
okay. Mhm.
Yeah.
And is your result basically classified as a model, or you can have coupling between any?
No, any 1D spin model. As long as the range of it can be like a 50, I don't know, 50 can be interacting together and they can be a million level, as long as it's fixed, all of these things don't make a difference for LH.
Yeah, you can consider arbitrary interaction, 50 spin, 100 spin, high order interaction, so on and so forth. But the point that the model will become only interesting if it have some kind of symmetry or based on some physical observation, no?
That's fine. I mean, they will also be, so the symmetry will not change the classification. You can like this classification more or less. You can think that it tells you something more or less deep or interesting about the models. It's just one way to look at them. Actually, what I want to share with you now is that this radical distinction between 1D and the rest is ultimately due to the fact that a string is a one-dimensional thing. So a push-down automaton can recognize, what will it do to recognize the language? It will read the spin, the configuration, and then read the corresponding, be adding the corresponding energies in the stack, and finally check whether the energy written on the string is the same as the one on the stack. That's okay, but for 2D, the push-down automaton will not be able to do the same because there are long-range correlations in the spin configuration because you've done something really violent, which is stretch out a two-dimensional configuration of spins in a string. That's something very unnatural, right? You need to go like a snake or something so that you can stretch it out.
You can also derive the 1D spin model with long-range interaction. So instead of nearest neighbor, you can consider next neighbor, so on and so forth.
That's fine with me. That will all land here. Because, as I said, if they're like, it interacts with the one that's 48 sides away, no problem. I mean, no problem for the classification, because all what matters is finite versus infinite, things like that. I'm not saying that makes sense.
Just because I'm not in this field, but I understand you use lots of binary data. What model that is derived by generating sequence of zeros and one would fall in the language hierarchy?
It depends on the sequence of zeros and ones. Some will be very simple, some will be very complicated. Most of them will even be outside, will not even be recognized by a Turing machine. So a formal language is generally just, maybe I can write over there. You have a pen?
Yeah, it could.
So a formal language is nothing but a subset of sigma star. Now sigma, imagine that it's 0, 1. And sigma star is the collection, if you like, of sigma n's for the union of all n's. And sigma n is the Cartesian product n times, right? It's the concatenation. That's the fundamental operation that you can do on string on such alphabets, right? So some L's are very simple. They are regular. For example, if they contain a pattern, they are regular. Imagine that I will take all L's that have something like, for example, I will write 0, 0, 1, 1, y, such that x is in sigma star and y is in sigma star. Okay, that's a pattern. So all strings that are anything contain this pattern and anything. That's a regular language. Or all strings that are multiples of 3 in binary. That's also a regular language. Or for context-free, they would be things like, and this is the standard example of context-free, 0n, 1 to the n. You need a stack to do that, to recognize that that's for any n. And then there are more complicated, and eventually here there's the halting language, if you like. And as I said, most of them are too wild to have a finite handle. Okay, and what we observe is that some of these are universal for us as spin models, some are not. For example, the 2D icing without fields is not universal, but the 2D icing with fields is universal, and they both fall here. Whereas this is not universal and this is. So that's indicating that something is off, or that this classification cannot help us much in comparing their universalities. It can help us some, but so Toby Reinhardt, who also worked on that, he would say that the notion of simulation among spin models is not nicely mapped to a notion of transformation between the LHs. Okay, but part of the kind of this work, we obtained that if we look at the Ising model and this new complexity measure, we find a new easy to hard threshold. Usually, you may know that for the computational complexity of the Gram-State energy problem, 1D and 2D is easy, that is to say in P, that 2D is in P is kind of a miracle by Lunzager. 3D is hard, and P complete. For us, 1D is easy, anything beyond 1D is hard.
That means where I solve the hard one, the 2D is hard in your criteria.
It's a different way to measure the complexity.
I mean, like the classic way, there's one in 2D, we know the solution, and at LNP, and 3D is not solvable. But in your new framework, only the 1D is easy, so the 2D is hard. Can you extrapolate that then if you solve one hard, can you solve all the other hards? Or like NP, P equal NP, like if you solve one NP, you solve all NPs? Or...
I like your question. So here, there's a wonderful notion of completeness, which comes from the notion of a reduction between problems, decision problems. We don't really have such a notion of a reduction here in terms of completeness. Never thought about that.
So no hope to solve the 3D Ising model. It's like last week he tried.
Yeah. I guess so. This is it's you can call this hardness or complexity, but it's also like power. And if you want to use an Ising model as an analog computer to calculate a function, it says that actually the 2D, even though it's easy to solve the ground state problem, you can use it to simulate complicated functions.
Its grammar is context sensitive.
Yeah.
Okay. Okay, and just to mention that Toby Reinfeldt derived an if and only if classification now of the Ising model. Now that's not for all spin models, but just for the Ising model. In the hierarchy, it is more detailed, and it goes into the details of how the family of graphs grows with n. And so in this case, we can have if and only if characterizations as opposed to the previous one. So we have just one direction. Okay, now it's pretty late.
I'm happy.
What should I do?
Yeah, continue. Yeah, sure.
Yeah?
Yeah, we have these.
How? 5 minutes or
No,
2 minutes?
yeah, take that.
Okay, so maybe I'll keep it short and we can leave more details for later on, okay? Okay, now comes the heavy duty. Okay, now we derive the categorical framework for universality. I'm not an expert on category theory. I will assume that you're not experts either, but I think this is hopefully will be understandable. Remember, our goal is to derive a theory of universality. Maybe the goal is too broad from the beginning. It's kind of doomed to fail, but we tried. I think some lessons are beautiful. Okay, so we have an object, which we call the simulator. Will have a property, may or may not have this property, called universal. But if it does, it is so because it encompasses all so-called targets, T, very abstract, right? In all contexts, C. So you can think of targets as functions and contexts as the input to those functions. And encompass, bear with me, it will mean something like simulates. So our object will be something like that. So this is to be read bottom to top. And so that's what we call the simulator, okay? So P will come in. P will be some programs, and C will be some context. They are objects in a category. And this will go through, so the programs will be duplicated, and first go through a transformation on the left, go through a transformation called a compiler, and result in something called targets. And the context, so, and then something else called context reduction will be fed both the programs and the context, and it will spit context. Okay. So maybe I should have started with the so-called trivial simulator. Okay, now this idea actually, let me. So like the stepping stone or like a fundamental role will be played by what we call the trivial simulator, which is in some sense, it's not a simulator at all. It is just all things. or more precisely, it is all targets in all possible contexts. So it is this entire target world that other simulators will be trying to imitate. This is okay, so this is just like T goes through, here it is deleted. That's something we can do in our category, and C goes through. Okay, sorry, and the trivial simulator is by definition universal because it is just everything there is. It is all targets in all contexts. The idea will be that something like that could be more economic and will pretend to be all of that. That will be like a non-trivial simulation. If this can pretend to be all of that, we will call that universal. And exactly what I just said. So a simulator is universal if for every target there is a program so that after a pre-processing, eventually, it behaves like the trivial simulator. So, okay, forget about that for a second. So just saying this object is universal if it can be programmed so that this will behave like it, like anything else. And maybe if you just take home one message from this third part, it is this. Sometimes you can pretend to be in more efficient ways than being. That's this entire business of universality, if you like. So, and let me point out that this relation of pretending to be will be different in the various examples we will consider. It could be equality after evaluating the target in a context. So obviously our key example is that of universal Turing machines. Consider our target will be partial computable maps. The context will be input strings. And they will be evaluated to give us reject, accept, or non-hold. There is such a thing as a universal Turing machine. That's what this looks like in this framework. The key is that the target thing, that's what I said at the very beginning, the target partial computable map can be fed as part of the input that's happening here and put together into a pairing function so that a fixed universal Turing machine can evaluate the description of the target thing together with its input and return the same result. For spin models, the targets are the Hamiltonians, set of spin systems, and the contexts are their spin configurations. And they can be evaluated to return an energy. And crucially, the behaves like relation is only equality below a certain energy, right? So the 2D Ising model with fields will be identical, its spectrum will be identical to the target spin model only when this is looked at beyond a threshold, below a threshold.
Can that threshold be arbitrarily high?
Oh, you can make very precise statements on that. You will have to pay kind of a price in terms of maybe coupling strength here and so on, but Toby Reinfeldt has made a very careful statement about that. Okay.
Sorry, can you explain the rest of the diagram so that then
So for a universal spin model, so how does it do the trick? The 2D Ising with fields will have more degrees of freedom. We used to call them auxiliary variables. Maybe in machine learning, they might be called hidden units. And you can tune their coupling strengths, and so that in the low energy sector it behaves like the target one. You can make the statement a lot more precise, but that's in essence what's going on. So the choice of coupling strengths will be like the program. Will be specifying what the Ising model is supposed to behave like a Potts model, like a lattice gauge theory, like a 4D Ising model, because it's inhomogeneous generally. Okay, hey, another way of pretending to be is by being dense, right? Like the rationals can pretend to be the reals. So that's another form of universality, if you like. Maybe the instantiation is not so crucial, but take a point in the reals and a precision. This, we don't have an input there, right? So that's a singleton. And map it to the open ball of radius delta centered around R. You can do the same if you would take the rationals as opposed to the reals, and you would consider subset inclusion. Maybe the details are not so crucial, but maybe interesting is that, yeah, being dense is a form of pretending, and therefore is a form of universality in this framework.
Does it also in like a mathematical setting like this, are there notions of unreachability and dense subsets? Like, are there reals that are never reached?
I have no idea. I don't know.
Are the real numbers that are not approximated by,
Exactly, yeah.
but they are, real numbers are defined as being approximated by the rational.
Exactly, that's what I'm confused.
So that's why they can't be unreachable.
I agree.
Yeah.
No,
I agree.
But before it sounded like there's like unreachability, so that somehow always comes with a notion. So it's always one item.
Not quite. We try to make it precise. Not quite.
Okay.
It may depend on the notion of universality. Yeah, thank you for your question. Yeah. Okay, maybe I'll speed up. Okay. Take an algebraic structure like a vector space. Well, then the basis of a vector space can pretend to be any point in the vector space. That's the whole point of a basis, right? Because any point can be expressed as a sum of a scalar times an element of a vector space. Okay, so that's also an example of universality. A generating family of an algebraic structure. It could be a vector space, it could be a group. If you have some generators of the group, then any element in the group can be expressed as certain product of generators. Maybe the simplest of them all is being on top of a preorder. Suppose that I have, I don't know, 5 numbers, 3, 7, 8, and 10, and pretending to be is given by being larger than. Then I can just take the largest number, 10, and it will pretend to be any other thing. Okay, and we can also derive some necessary conditions for universality. For a suitably monotone function, if S is universal, the supremum of the image of the compiler and their phi is the most. Maybe. So one consequence is that for spin systems, we can conclude that no finite spin system can be universal. A spin model can be universal. Spin model is a collection of spin systems. Maybe this sounds a bit obscure, but really I'm trying to illustrate that one can do things with a framework beyond examples. And then you can talk about parsimony, or you can talk about how cool or how efficient somehow a simulator is, or how resourceful. So if it needs very little to generate everything, then it's very parsimonious. So the trivial simulator would be, in this sense, the worst. And then we proved that the singleton universal simulator, so a universal Turing machine. So there is the universal Turing machine is strictly more parsimonious than the trivial simulator. That's like some business with the categories, and then there was the proof that there was a map from one to, like, one could be transformed to the other, but the other not to the one. So maybe you're all tired, but now comes Lovier. Should I explain it, or maybe everyone is tired and I jump to the conclusions? I
You
jump to
can
the
try, we can using an example every time you get back to the real world.
You said back to the real world?
Yeah, you
Makes
keep
too much
hiding,
sense.
sorry, yeah, I'm sorry.
Okay, so what is universality? One way to see it is that it is a form of a complete parameterization. So suppose that you have a function f that goes from p cross c to b. Then we will say that it is a complete parameterization if for every g that goes from c to b, so note that g, the domain of g is smaller, it's only like the second half of the domain of f. So for every g, there is something in p, a c sub g, you see, it can depend on g, c sub g in p, so that if you fix that c sub g for f, and you let the other variable free, then f and g are the same. Okay? So f is a complete parameterization if for every target g, there is something that you can fix in the first variable so that they will be the same. That is a form of universality, right? F can pretend to be G.
Partial derivatives are.
Not sure about partial derivatives, but it's late, so let me move on. And now I can state Lovier's theorem. Now, if F, now consider an F that goes from C cross C to B. So the first part is now C as well. Now, if you claim that there's an F, which it's special right now, so from C cross C to B, which is a complete parameterization, then every alpha from B to B, so every map from B to B has a fixed point. This is the contrapositive of Lovier's theorem. This is stated in terms of a fixed point. So, in other words, if this is a complete parameterization, then you cannot have very interesting functions on B. Like, generally functions need not have a fixed point, but that's stating that every such map, homomorphism or whatever, I say function, but I mean map homomorphism, will have a fixed point. In plain words, they cannot be too expressive. If you have a complete parameterization, this will fall short somewhere else. The tension between universality and unreachability should be kind of expressed here.
Is this something that said? Is this an interesting property of B, F, or C? What does this put?
This is a shortcoming of this collection of things.
Of both. Okay.
Is this some related to any kind of other fixed point theorems, to Rauer or?
Question, I don't know, maybe I should know. By the way, the contrapositive will read something like the following. If you have something of this sort and a function on B without a fixed point, like negation, then there can be no complete parameterization.
It's a bit like platform alternative, but then different.
Like what?
Platform alternative.
I mean, let it.
Let's give it to,
Yeah.
Okay, so then now that's the contrapositive. If there's an alpha without a fixed point, there cannot be a complete parameterization of the set of functions. And so that's how Janowski puts it. So G is unreachable if it cannot be represented by a CG. So, and the idea is always that what's reachable from F will be very small. Most of it will be outside, will be unreachable. Like you can see this as the image of the natural numbers when they are trying to reach to the reals. That's very small, most of it is outside.
Right. So this is basically saying if your universal object, whatever it is, if it's a Turing machine or spin monitor or whatever, if that exists, then there's also unreachable things.
Yeah, for example, universal Turing machines exist at the expense of having uncomputable problems.
And what would be the expense for
For spin models?
for the way you define this universality?
Well, that's a relation, that's all I can say. Because the framework is so general that all I can give you is a relation. I think I have something. I can give you this relation.
So what would be an uncomputable spin model?
No, I don't know.
Okay.
Again, I think that they are different. I don't know about if I can construct such things. Okay, maybe that's too much. Okay, so thank you for bearing with me for so long. I have been trying to share with you some of our attempts to understand some of the scope of universality and unreachability. And maybe I mentioned that Toby Reinhardt just proved that spin model universality is indeed the same as the universal approximation theorem, where one can be derived from the other, and the other from the one, for restricted Boltzmann machines after long suspecting that this was the case. And I'd like to end by celebrating that he just defended his thesis last week, and he did a great job. That's great news. Thanks.
Well, let's take a few minutes for questions, but not too long. And then we can go down for lunch, but I'm sure everybody's hungry. Any direct ones?
For the case of the ID model, that means your parameterization is a map to the 2D ID model. And what would be unreachable?
I don't know.
Okay, sorry, I'm repeating the same thing, but what would be them?
Larry?
I'm not sure exactly what you mean by spin model, because you gave example of 1D, 2Dizing, like what is a spin model here?
Thank you. It took us quite a while to figure out, because this is just different conventions in every paper. For us, it's generally an infinite family of spin systems, and a spin system is a function which has from spin configurations that a finite number of them, finite and fixed, to the reals. So it's an infinite collection of functions, each of which has a finite domain.
Mm-hmm.
And generally this collection is well formed.
But it's not possible to get a complete parameterization of this? I mean, it should be possible.
The short answer is I don't know. I mean, it can be instantiated as in our framework, but I don't know what the consequences are.
I have one final question, maybe. So you have this statement that says finite spin models cannot be universal.
Mm-hmm.
And there's sort of the analogous statement for other universal objects as well, like that put limitation on what they can. What would it be for a Turing machine? Is there something like with a finite tape cannot be universal?
Well, with a finite tape, for sure not.
Exactly. Is that the direct analogous statement?
Don't know. That's a good question. I don't know. Perhaps instead of a finite tape, what may be meaningful is to consider a machine that cannot use more cells than the ones used to write the input.
Okay.
And this is called a linear bounded automaton. And these do not have, there's no such thing as the universal linear bounded automaton. There seems to be a form of pseudo-universality, a weaker statement of the sort. For any target linear bounded automaton, there will be a pseudo-universal universal LBA that will simulate it. As opposed to in Turing machines, the quantifiers are in reversed. So you say there exists a Turing machine such that for any target machine, the first one will be able to simulate the second. So maybe for LBAs, there's a statement that kind of grows with the size of the target LBA. But I don't know, your question.
Okay, maybe we should have for lunch then.